Okay, we were looking about partial derivatives. So we established the application of partial derivatives as finding maxima minima of two variable functions, correct? So what we established, we followed some notations. Fx means dou f by dou x, fy means dou f by dou y, fxx means dou square f by dou x square, fyy means dou square f by dou y square, fxy means dou f square f by dou x dou y, and we wrote that fx should be equal to 0, fy should be equal to 0. Then we established three cases, right? First case is fxx less than 0, fyy less than 0, and fxx into fyy minus fxy the whole square is greater than 0. Then the second case was fxx greater than 0, fyy greater than 0, fxx fyy minus fxy the whole square is greater than 0. Third case was fxx fyy minus fxy the whole square less than 0. This is the condition for maxima, this is the condition for minima, and in this case we say that it is a saddle point. This is neither a maxima nor a minima. This is neither max nor min. Okay, so these are the conditions, and we also established that this is called the discriminant. This is referred by the name discriminant. Okay, now let us take quick problems and solve it. Okay, example 1. f of xy is xy minus x square minus y square minus 2x minus 2y plus 4. Okay, this is what is given. Find the extremum values. Extreme means what? It is referring to max and min both. Okay, these are the two extreme values, right? So for that we have to find all the points. We have to find all these things. What is fx? What is fy? What is fxx? What is fyy? And what is fxy? What is fx? Fx is nothing but dou f by dou x. This is nothing but differentiation with respect to x alone. I am treating y as constant. That means I will get y minus 2x. X square on differentiation will give 2x. Y square on differentiation will give 0, because it's a pure function of y and we have differentiating partially with respect to x. 2x will give me minus 2, 2y again will give me 0 because it's a only function of y, 4 will again give me 0. So this is what I am left with, 2x, y minus 2x minus 2. Again I will get zeros after this, 0 plus 0. And fxx will give me minus 2. Okay, and fyy, we have to find fy first, right? Fy, what is fy? Dou f by dou y, correct? This is nothing but xy on partially differentiating with respect to y will give me x square is a purely a x term, so differentiating partially with respect to y will give me 0, y square will give me minus 2y, then minus 2x is a pure x term that gives 0, minus 2 plus constant is a 0. What is fxx? On the first go, fxx is nothing but dou square f by dou x square. This is nothing but dou by dou x of dou f by dou x, correct? Similarly, fyy is nothing but dou square f by dou y square. This is nothing but dou by dou y of dou f by dou y. So this will give me this will give me I have to differentiate this now partially with respect to y to get this, correct? This is what it is. So now I will get minus 2 here again. Observe that fxx and fyy are negative, not negative functions, they are negative numbers. Okay. Then what is fxy? Fxy will be differentiating this with respect, this is nothing but dou by dou x of dou f by dou y, correct? So I have to take this and differentiate it with respect to x. You will get 1. So the first condition we have to check is fxx into fyy minus fxy the whole square should be greater than 0. This is common condition for both maxima and minima, correct? So this will give me minus 2 into minus 2 minus 1 square. This is 3, which is greater than 0. That means a valid maxima or minima will exist, correct? Now for the condition for existing maxima minima is what? Fx equal to 0, fy equal to 0. This will imply that y minus 2x minus 2 equal to 0, and this will imply that x minus 2y minus 2 equal to 0. Correct? So we get that x minus 2y equal to y minus 2x. On simplifying, making the like terms together and all, we get x 3x is equal to 3x equal to 3y implies x equal to y. We get this is one result we get, correct? This is the result we are getting, correct? And x equal to y is a one result we are getting. Now we have to find the value of what is that x or what is that y, correct? Because here all this is also equal to 0, this is also equal to 0. By simultaneous linear equation method we found that, correct? And what is that value now? On simplifying we will find that x is equal to y is equal to minus 2. It's just I am taking these two equations and solving it by simultaneous linear equation method. I will get x equal to y equal to minus 2. Correct? That means for x equal to y equal to minus 2, fxx is 0, fx is 0, fy is 0, and fxx, fyy minus fxy the whole square is greater than 0. So minus 2 comma minus 2 is a maxima for this function. This is the answer. Let us solve one more quick example. F of xy is equal to x into y. Find the extreme values. Okay, this is another interesting question to solve. Okay, now what is fx, what is fy, what is fxx, what is fyy, what is fxy? These are the questions we need to answer. What is fx? This is dou f by dou x, nothing but y. And fxx is nothing but dou x square by dou x square. This is nothing but dou by dou x of dou f by dou x. I am writing this every time so that we understand it very clearly without any confusion. Dou f by dou x is y. Y on partially differentiation with x will give me 0. Fy will give me dou f by dou y. This is x. And fyy will give me dou by dou y of dou f by dou y. This is nothing but dou by dou y of x. This is nothing but 0. I am partially differentiating x with respect to y. That means it will give me 0. And what is fxy? Fxy is nothing but dou square f by dou x dou y. This is nothing but dou by dou x of dou f by dou y. This is nothing but dou by dou x of x. This is nothing but 1. Okay. Now first thing, always remember, whenever we are having these two variable functions, check for what? Discriminant greater than 0. Okay, this is very important. Because why we are doing this? Because discriminant, I am writing a short form, discriminant less than 0 means no maxima or minima will exist. Correct? This is very important point. So what is discriminant? Discriminant is nothing but what? Fxx into fyy minus fxyz square. This is nothing but in our case fxx is 0, fyy is 0, fxy is 1. So we get minus 1, which is less than 0. So discriminant is less than 0 means the function neither has some maxima or a minima. This is very important. So what is that we are getting? We will get this type of points are called saddle points. Correct? So what is that saddle point we have got? Fx is nothing but y and fy is nothing but x. When we equate it to 0, we get x is equal to 0 and y equal to 0. So 0 comma 0 is a saddle point. This is very important. This is the answer for this problem actually. There is no maxima or minima existing. We have only a saddle point at 0, 0. Okay. So we have seen in calculus, so far we have seen only differentiation. We saw differentiation in detail. Then from differentiation we move to partial derivatives, and we saw application of both of them. Having completed all these things, let us move towards integral calculus. This is very important part and the other part of the calculus, integral calculus. The integration operation is defined as the reverse of differentiation. In differentiation, what we did? In differentiation, we were splitting it. That is infinitesimally small pieces we were taking. Correct? This is what we did in. Okay, this is not clear, I think. Let me write it. Infinitesimally small pieces we were taking for differentiation. Now we add those small pieces and reconstruct f of x from f dash of x, and this operation is called integration. It is denoted by this symbol. That is, the idea of integration is the reverse of differentiation. That is, if I integrate f dash of x, I get f of x. And if I differentiate f of x, I get f dash of x. So what happens? D of f of x is nothing but f dash of x dx. On integration, d and f are inverse operators, so they get cancelled. So I reconstruct back f of x. So f of x is nothing but integral of f dash of x dx. This is what we call it as integration. Fine. Okay. Now let us see integration of some standard function. So integration is not so friendly like differentiation. We need to have special techniques for that. So let us list the techniques. First technique is reverse mapping. What do I mean by reverse mapping? That is, we reverse map with the derivatives. That is, I know that differentiation of sin x is going to give me cos x dx. Correct? So if I integrate cos x dx, I will have to integrate this. So this cos x dx on integrating will give me sin x. Correct? This is the conclusion. So cos x on integration will give sin x. Similarly, we can keep on extending the idea. This is, we were discussing about the idea of reverse mapping. So the first thing we saw was cos x. Similarly, we can say differentiation of cos x is minus sin x. So cos x, differentiation of cos x is nothing but minus sin x dx. So integration of minus sin x dx is d of cos x, like nothing but cos x is equal to minus integral sin x dx implies integral sin x minus cos x. This is one important result. Similarly, we know that integration of, we start with the differentiation, right? Differentiation of x square is 2x. Correct? So differentiation of x square is 2x dx. Sorry. So if I integrated both sides, this and this will get cancelled. X square is equal to integral of, therefore integral x dx is nothing but x square by 2. It's an important result. Okay, let me extend this. Differentiation of x power n is equal to n x power n minus 1. Correct? Okay. That means differential of x power n is equal to n x power n minus 1 dx. If I integrate both sides, what will I get? I will get x power n is equal to n integral of x power n minus 1 dx, or can write it as x power n by n is equal to integral of x power n minus 1 dx. Correct? Or in other words, I can say integral of x power n dx is equal to x power n plus 1 by n plus 1. Correct? Either way I can say. Correct? Here I am just replacing this n minus 1 by n. If this n minus 1 is becoming n, this n is becoming n plus 1 here. Both are same. Correct? I added 1 here, I correspondingly modified these terms also. Correct? Fine. Now, the moment I do this, I am dividing. What I am trying to do here? I am dividing by n plus 1. That dividing by 0 is not allowed. Correct? So the assumption is n plus 1 cannot be equal to 0. That is, n cannot be equal to minus 1. If n equal to minus 1, the above formula cannot be, the above result cannot be applied. Please remember that this is very, 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 very important. This result cannot be applied if the value of n is minus 1. This is very important. Okay. We were seeing integration technique by reverse mapping. Correct. This was the first technique. Here we saw that. The second important technique, because integration is not so straightforward like differentiation, is substitution. This is very, very, very important technique, and there is one important rule for this. There is no golden rule. There is no golden rule for substitution. It is by analyzing the given problem only. Means what? I cannot find a trick which can be applied across every problem. Substitution suitable for one problem need not suit the other problem. Please remember this. This is very important because there is no golden rule. It is not true because there is no golden rule. And it comes only by practice. There is no secret or there is no secret ingredient. Okay? Fine. Okay, let us take an example. What do we mean by this? Okay? Fine. Now let us take the example of tan x. I have to integrate. I have to find integral tan x dx. How to find this? See, unfortunately, there is no derivative whose result is tan x. Correct. See, how do we integrate? How did we find this? Integral sin x, how did we do? Integral sin x dx, we found it because differentiation of cos x gave me minus sin x. So, sin x dx. So, upon integrating, I found that integral of sin x dx is nothing but minus cos x. Like this, I reverse mapped it. Correct. But unfortunately, there is no differentiation whose result is tan x. Unfortunately, there is no differentiation. Rather, I will not say no differentiation. No, I will use this standard differentiation whose result is tan x. So, I am unable to reverse map it. I am unable to reverse map it. What to do now? Now, let us find a way out. Tan x can be written as sin x by cos x. Correct? Okay, now let us take this. Now, if I put sin x integration of tan x dx is nothing but sin x by integration of sin x by cos x dx. And observe that the differentiation of cos x is sitting here. What is differentiation of cos x? It is minus sin x dx, correct? So the derivative of denominator is sitting in the numerator, correct? Here, derivative, there is a minus sign there, don't worry about it, we will handle that later. Derivative of denominator is present in numerator, correct? This is a very important observation. Observe this. This is very important observation. Please observe this. Okay. So, if I write cos x, for example, substitute cos x as t. So what will happen if I differentiate both sides? Differentiation of cos x will become dt. And what is differentiation of cos x in turn? It is nothing but minus sin x dx is dt. So if I put this substitution here, what will be the result? The result will be something like this. It will be integral of tan x dx is equal to integral of sin x by cos x dx. This is nothing but I am substituting cos x as t and sin x dx is nothing but dt. So I will get minus dt here. Correct. So minus is outside. I will get dt by t. Correct. And what is integral of dt by t? It is nothing but log of t. There is a minus symbol outside. There is a minus outside. And log of t will give me what? It is actually log of mod t. Okay. Log of mod t. Well, let me write it clearly. It is minus log of mod of t. Okay, so this is nothing but minus log. What is a log b? A log b is nothing but log of b power a. Correct. So similarly minus 1 log t will be log of t power minus 1. This is nothing but log of 1 by t. Now t is a parameter which we have introduced, so we have to remove that also. So I know that t is equal to cos x. So 1 by t will be secant x. Correct. 1 by t will be 1 by cos x. That is nothing but secant x. So therefore integral of tan x dx is nothing but log of mod of secant x, and we get always a constant. This is I am writing because let us see why I am getting this constant. This is also a good observation. Let us see that. This will come for every integration, not only for this integration. So far the integrations what we have seen by reverse mapping also, this constant will come because why is that c coming? Why c comes? In integration is the question. In integration. Okay, this is okay. What is this? Why c comes in? See, for example, let us take f of x is equal to x square plus 4. Let me take another function g of x is equal to x square plus 7. What is f dash of x? 2x. What is g dash of x? This is also 2x. Let me take some h of x, which is just h of x. Let me take some h of x, which is x square. Okay. And what is h dash of x? H dash of x is also 2x. So either all these cases we are getting same thing. Now h dash of x upon integration also will give you x square. G dash of x also upon integration will give you x square. F dash of x also will upon integration will give you x square, because derivative of a constant is 0. Correct. Derivative of a constant is 0. Derivative of a constant is 0. Correct. So when we integrate 2x, we don't know what is this constant. It might be 4, it might be 7, it might be 0, it might be minus 2, anything. So we don't know we don't know what is the constant. So we just add an arbitrary constant called C, and this C would be evaluated using boundary conditions if present. If given, okay, if boundary conditions are not there, you need not worry about this. Okay, fine. Now we will introduce one very important result. What was one important observation we made there in previous problem? In previous problem, that is integral of tan x dx, we observed that the derivative of denominator is present in numerator. What is the advantage of this structure? That is, I have a structure in which the derivative of denominator is present in the numerator. Can I take any advantage of that? The answer is yes. What is the advantage? Let us evaluate that. Let me take an integration of f dash of x dx by f of x. If I have an integration like this, I have a function f of x whose derivative is present in the numerator. Correct? Now what is the advantage of this structure? Let me substitute, let us substitute f of x. I am not substituting for x, I am substituting f of x as t. I am not substituting for x, I am substituting f of x as t. Please remember this. Okay, I am not substituting for x. Okay, please remember this. I am substituting, let me write this clearly. I am substituting f of x as t. So what will happen to this integral f dash of x dx by f of x will become what? F of x is becoming t, f dash of x dx will become and I know the result of this integration. This is always log of mod t plus c. And what is my t? It is nothing but, because t is a variable which we have introduced it. So it is our duty to remove it. Okay, so how do we remove it? What is t? T is nothing but f of x plus c. This is a very, very important result. So the moment I have the derivative of denominator in the numerator, the answer is log of f of x plus c. This is an important result. So we have seen that if the derivative of denominator is present in the numerator, we have a very powerful structure in which we substitute the denominator as a parameter and the derivative will be in the numerator. So we saw that integral of f dash of x dx by f of x is nothing but log of f of x plus c. This is a very important result. Okay, this is very much useful in integration. Okay. Okay, first let us see some examples for this. Integrate secant x dx. Again, there is no standard differentiation whose result is secant x. Correct? So direct reverse mapping is not possible. But we can find a way out. What is the way out? Yes, we are going to do some simplification here. Sort of sec x dx. Let me multiply and divide by secant x plus tan x. Why I am doing? There is a reason for that. If I multiply and divide by sec x plus tan x, there is a reason I am doing this. Why? Because what is the derivative of, okay, let me see this. What is differentiation of secant x plus tan x? This is nothing but secant x, differentiation of two functions, sum of two functions will be same differentiation of the individual functions summed up together, correct? So it will be differentiation of sec x, differentiation of secant x plus differentiation of tan x, then I will get a dx at the outside commonly, correct? What is differentiation of sec x? Okay, rather let me write this way. Differentiation of sec x will be secant x tan x dx plus differentiation of tan x will be sec square x dx. So here I have one secant x, here I have one secant x. If I group and write, I will get secant x into secant x plus tan x. One second, sorry for the confusion. It will be secant x into tan x plus secant x dx. And what is this? This is the term sitting in the numerator, and where I started with, this is the term I started with, this is the term sitting in the denominator. So by multiplying with multiplying and dividing with sec x plus tan x makes the derivative of denominator present in the numerator. This means I have integral sec x into sec x plus tan x dx by secant x plus tan x. The derivative of this is here. So I can substitute secant x plus tan x as t. Therefore dt will be sec x into sec x plus, is nothing but, by this substitution, if I do this substitution in this integration, I will get this result, dt by t. This is nothing but log of mod t plus c. That is nothing. Therefore integral of secant x dx is nothing but log of secant x plus tan x. This is very important.